All right, and why this one never closed, did it? Ooh, that's the problem. Okay. Never closed the last one. That was what my deal was. Alright, we are now recording, so let me get my go from the correct slide. Alright, first and foremost, you already voted. Way to go. On the way home. Please say yes. Please vote. Okay. Oh, let me mark the roll. I forgot to do that. I knew there was something. Okay. Walter is here. Gavin's not. Dawson is. Andrea is. Josh is not. Jake's not. Allison's not. Chris is here. Okay. 1, 2, 3, 4. Okay. Even though I don't have a little badge on, I did vote on my way in this morning. It was such a hectic place there that I forgot to pick up the sticker. So there was a woman ahead of me with 3 kids. They were all milling around the places you're supposed to put your ballot in, and one of them was sticking pins there and stuff. And I thought, don't break the machine, you know. And the poor poll worker was trying to be very polite about it, trying to keep away. The woman wanted all her kids to have I voted stickers on, so she was doing that. And she forgot to give me one, so, and I forgot to ask for one. So sorry, it was crazy, but it was nice seeing that bigger crowd there. And I appreciate that the woman was getting her kids fired up about voting, even though they were being a pain. Yeah. Okay, all right. So please vote. Now, here's one other announcement. I forgot to do this one this morning. Normally on Thursdays, I have office hours from 11:15 when this class is over with until 3:15. Not this Thursday. Okay, today I do 11:15 to 3:15. But on Thursday, we have a faculty meeting. Fortunately, it's on this campus right over here in Alpha Hall Auditorium, and I think it starts at 2:30. So I have to leave my office before 2:30 to get over there by 2:30, and then I come back at 3:15 to teach my class. So I will be out of the office for that little bit of time, about 45 minutes out of my office hours. I won't be there. Okay. Can't think of any other announcements. I will say this. I finally have finished, I think, everything I need to do, or at least everything I need to know. I know that I need to do about the spring schedule. Finally, that's over with. So that's out there correct. I hope it's correct and everything. Which means, I've already started doing this, whittling down the piles of papers that needed to be graded. I've got everything from this class graded. I don't have it on Blackboard yet, but I've got it graded. So if you need to see scores, you certainly can and see the test. But I'm going to be spending just about all my remaining office hours trying to get the grading caught up. And when I get the grading caught up, Jayla's here, I will then start getting grades on Blackboard. Okay. Any questions? Anything we've done so far? Okay. If not, we're on page 384 with Chapter 5, Analytic Trigonometry. Oh, they keep coming. That's good. Josh is here. All right. If we could just get... Allison's missed a while. Do you know if she's going to be back? Allison? Okay. She was very close to perfect attendance. In fact, was perfect attendance up until last week. I thought she or one of our students said they were going to be out of town for a week. Is that not her? Or you not? All right. Hopefully she'll be back. Good deal. And I hope Jake will be coming in soon. All right. So we were page 384 Analytic Trigonometry, Chapter 5. 5.5, the last section in analytic trigonometry, multiple angles and the product sum formulas. We've already done the double angle formulas, and it talks about how to do triple and more higher order multiple angles. And now we're going to do the half angles, which are related sort of to the double angle in a strange kind of way. And then we'll do some of the others in the last half. Now, what I said preceding the previous section, I didn't mean there. Those things you do use a lot, okay? It's this section. The first part you use a lot, like the double angle formulas, sometimes the half angle formulas. Then as you get into these other ones here, you use them less and less. So I never bother with memorizing them. I just, if I need them, I'll look them up, okay? Or remember how to derive them, and that's just about as easy. Now, if my memory's right, and it's not always, let's go back. How did this happen? I close this out. There it is. Okay. This is the one. Wow. Okay. Now, here's where we are. We did the sine, half angles formula for sine last time. Everybody remembers that, right? Yes. Okay. So vivid in our memory. Okay. We hadn't done the one for cosine, but it was very, very similar to what we did for sine. So let's refresh our memories and redo how we got this cosine. And it's all pretty related to, in some senses, kind of to the double angle formula in a strange way. Let me get my thing back up. All right. In the double angle formula, remember there are three different ways to express a cosine 2a. Okay? Oh, let's make it 2u since that's what they're using here. 2u. Can anyone tell me what some of those are? What's cosine 2u? Happy cosine 2u. Oh, it was so long ago. At least 5 days. Cosine 2u. Help me. Cosine squared u minus sine squared u. Okay? That certainly is one. But that has both sines and cosines in it. Let's do one that has only cosines. What's another one that has only cosine? Cosine 2u is equal to basically what it is, take the Pythagorean theorem that we know and love so much. 1 is equal to cosine squared u plus sine squared u, right? Add these two together, you lose the sine squared u's, and you get cosine 2u 1 plus cosine 2u is equal to 2 cosine squared u, and then subtract 1 from it, so you get a minus 1. Cosine 2u is equal to cosine squared u minus 1, right? All right. Now, I wish I had stuck with a now that I think about it. Let me go back and make those a's. Cosine 2a is equal to cosine, or 2 cosine squared a minus 1, right? Now, let's change the A to a U. Let 2A equal U. So now this would be, then, if that's true, then A is equal to U over 2, right? Follow that? All right, so this would then be cosine U, because 2A is U, is equal to 2 times cosine squared A, but A is U over 2, minus 1. Oh, let's take that 1 and add it back to the other side. And now you have 2 cosine squared U over 2 is equal to 1 plus cosine U. And what you do from here, divide both sides by 2, and then take a square root. And cosine U over 2 is equal to plus or minus the square root of 1 plus cosine U over 2. Okay. Now, that's how you get these half-angle formulas. Do we ever really need them all that much? Well, not too often, but we do occasionally. Now, what do you do with that plus or minus sign? Where does that come into play? Well, if this is what you're looking for, U over 2, you know what quadrant it's in, right? And if it's in the first or the fourth quadrant, you use the plus sign. If it's in the second or third quadrant, you use the minus sign. Because the cosine U over 2 could either be positive or negative. Just use the sign for the appropriate quadrant. Okay. So that gave us sine U over 2 and cosine U over 2. Okay? How in the world do we go about getting tangent U over 2? Well, on the one hand, it seems like it would be okay to divide those two. So that seems like it's a real pain in the neck, or some other body part. But if we go back to our tangent 2U formula, that doesn't seem to be very helpful either. So rather than go through a lot more than what we did just to get cosine half-angle formula, frankly, I'm not sure that I can ever remember using the tangent half-angle formula. If you ever need it, look it up. Now, here's the deal though. Which of these do you use? Okay? Whichever one you want. It doesn't matter. These are completely equivalent forms. Okay? If you were to cross multiply these two, you see that sine squared U is equal to 1 minus cosine squared U. That's always true. So these are exactly equivalent forms. Use whichever one you want. It's easy enough to use. Okay? And like I've already said, the signs that you use for the sine and cosine of the half-angle formulas depends on which quadrant. Tangent, you don't even have to worry about that. They work out for you by themselves. Okay, so those are our formulas for the half-angle calculations. Let's actually use some. Example 5. And here it is. Find the exact value of sine of 105 degrees. I don't know what sine of 105 degrees. That's not one of our favorite angles. So what in the world can we do with this? They want an exact value, not something that you pull off the calculator. Now, let me give you a hint. That double angle formula is not going to help you here, because that's not 2 times anything. It's 2 times 52.5. I don't know what 52.5 degrees is either, so that's not going to help us. But guess what? Yes, if you double that and make this the half angle, what is double 105? There you go. 210. Hey, I think we can do something with 210 besides mark check present. What can we do with 210? Do we know it? Yeah, 210 is, okay, that's 90, that's 180, 210 is 30 past 180, right? So there's the reference angle, 30 degrees down here. And I think we can deal with that. Okay? So what we're going to say is that sine of 105 degrees is the sine of 210 degrees divided by 2. The half angle formula. And what was our half angle formula for sine? Over 2. Is that what you said? All right. And the theta here would be our 210. All right. So what we need to do, though, before we get going too far, 105. Where is 105? I showed you where 210 was, but where is 105? Second quadrant. It's between 90 and 180. And what is the sign in that quadrant? Positive. So we forget about the minus sign here. So what we have is the square root of 1 minus, and what in the world is the cosine of 210? Okay, what sign was that? No, SIGN sign. Negative, because that is 210 is in third quadrant, cosine is negative down there. Okay, so it'd be minus that over 2. All right, if I could read my writing here, that would be helpful. That's the square root of 1 plus square root of 3 over 2 all over 2. Well, let's clean that up a little bit. Let's multiply numerator and denominator by 2 over 2, okay? That's legal, right? Because 2 over 2 is 1. Okay, so this would give us the square root of 2 plus root 3 over 4, right? Which in my calculation would be 1/2, because the 4 in the denominator, that can come out the square root of 2 plus root 3. Now that's an exact answer. Not a very pretty answer, but it is an exact answer. Okay? They write it over it. Square root of 2 plus root 3, all under the square root sign, over 2, or 1/2 times that. Does that make sense? Now, who cares that you give an exact answer? What they want you to do is think through it. That's the interpretation of exact value. They want you to actually work it out using the formulas. Because I look at that and I don't know anything more about what the sign is, because that's a miserable thing to try to think through what in the world that is. If you really were looking for that, you'd want something that you could approximate as a number. But they're just trying to get you to do that. So that's how we did it. Let's see how they did it, which I think is going to be pretty close. Begin by noting that 105 is exactly half of 210. So then using the half angle formula for sine of u over 2, the fact that 105 lies in quadrant 2, you have that sine of 105 is positive square root of 1 minus cosine 210 over 2, and that would be 1 plus root 3 over 2 over 2. And then if they didn't show how they got this, but if you multiply the numerator and the denominator by 2, you get that. The 2 now is not under the radical. This 2 is under that radical. This 2 is outside of that one, because when you multiply by 2, it made it 4. Square root of 4 is 2, so it comes out. The positive square root is chosen because sine is positive in quadrant 2. Good deal. Any questions on that? What made this go from a minus to a plus is that cosine is negative in quadrant 3, and that's where 210 is. So that's why the minus times a minus became a plus. All right, any questions on that? Now, before we get the product to sum formulas, there is example 6. Let's go back and do that as well. Okay. Find all the solutions of this. 1 plus cosine squared x is equal to 2 times cosine squared x over 2 on the interval 0 to 2 pi. Not counting 2 pi, getting right up to 2 pi, but not counting it. Okay? Where would you begin a problem such as that? Okay? That may not be a bad idea, but the problem is, I take it that by doing that, you're going to try to group like terms or something like that, right? These are not like terms because this is cosine squared x, this is cosine squared x over 2. You've got to get the arguments to be the same. And how can you do that? No, that's inside an argument. You don't just go around doing that. You got to use the conversion, what cosine of x over 2 is, and plug that in. That will get you back to cosine, right? So remind me what cosine x over 2 is. The half angle formula for cosine. Plus or minus the square root of 1 plus cosine squared x, right, over 2. Is that right? I'm going from memory. No, not squared. Just cosine. Yeah, sorry about that. Well, I can't get my eraser to come up. There we go. 1 plus cosine x over 2. Yeah. All right. So what do we have in this one down here? You have cosine squared x over 2. So what does that do with your, to this? What then is cosine squared x over 2? Yeah. In other words, you lose the sign for sure, because plus times plus is plus and minus times minus is plus. So those go away. It's going to be positive. And what happens when you square a square root? It goes away. So this is 1 plus cosine x over 2. All right? But you don't just have cosine squared. You have 2 cosine squared. So you're going to take this and multiply it by 2. And what does that do for you? Lose the 2's, right? If you're Dr. Seuss, you would love that, okay? So what is this 2 cosine squared x over 2? It's just simply 1 plus cosine squared x. What? That's not a squared, okay. That was from the 2 from above. Sorry about that. It's just 1 plus. So we got 1 plus cosine squared x is equal to 1 plus cosine x. Right? Now we want to solve that. What would that yield for us? Subtract 1 from both sides. They go away. And now you have cosine squared x is equal to cosine x. Well, to make that easier to do, now get it all on one side. What would that be? Help me. Cosine squared x minus cosine x is equal to 0. Now we're ready to what? What's the F word? Factor. Okay. How does that factor? Cosine x. And what do you have left? Cosine x minus 1. And that product is equal to 0. What does that tell you? Either help me, somebody. Either cosine x equals 0 or cosine x minus 1 equals 0, which means cosine x equal, help me, equal 1. Perfect. Okay, let's deal with each of these separately, just on the interval 0 to 2 pi. Where on the interval between 0 and 2 pi is cosine x equal to 0? It says x equal pi halves. Anywhere else? 3 halves pi. Okay, perfect. Okay. Now, where in the world in the interval is cosine equal to 1? Second? Well, it is barely. Cosine 0 is 1, isn't it? So x equals 0. The next place would be at 2 pi, but that's not on the interval. Okay? So that's it. At 0, pi halves, and at 3 halves pi. Okay? And I think you see that there. Oh yeah, there they have it. X equals 0, x equal pi halves, and x equal 3 halves pi. And they even show the little graph, the graphical solution there, and that would be at x equals 0, x equal 1.5707 blah blah blah, which is pi halves, and then one more time at where we know to be 3 halves pi. Again at 2 pi, but that's just outside the interval. Okay. Make sense? All right, good deal. So let's move on to product to sum formulas. Okay? Now, these come from a combination of places. Okay? Let's go back to sine of u plus v. Remind me what that is. Sine v. How about sine u minus v? and cosine, that's a pretty ugly C, of u plus v. Sine u sine v, and cosine u minus v. Cosine u, cosine v, plus sine u sine v. All right, we got them. Okay? Now, the first one they want there is what? Sine u sine v. The only place we see that are these two places here. Okay? So if we took the bottom one and subtract the top one from it, you lose these two, right? Take the bottom, subtract the top from it. Those two are identical. So then you have, and when you subtract them, you have 2 sine u sine v. If you do this minus that, minus and minus is plus, so you get 2 of those, is equal to cosine u minus v minus cosine u plus v. And then what you do is divide by 2. Okay? Or put the 1/2 in front. And you'll see that's your first product of sum formula. To get cosine u cosine v, you add those two together. So cosine u cosine v would be 1/2 the sum of those two. Cosine u minus v plus cosine u plus v. Okay? To get your sine u cosine v, those show up in these two, so you add those two together and you get sine u cosine v is equal to, these two go away, 1/2 sine u plus v plus sine u minus v. Doesn't matter which order you write them. Okay? And to get the cosine u cosine v, you subtract those two. And you see all 4 of those show up here. That's exactly what you got. Each of the following product of sum formulas can be verified using the sum and difference formulas that we got way back in the last section, 5.4. And sine u sine v is the difference of cosine u plus v and cosine u minus v. Not that word, minus v plus v. Half of that. And cosine u cosine v is 1/2 of the sum of those two. Sine u cosine v is 1/2 the sum of sine u plus v and sine u minus v. And cosine u sine v is 1/2 of the difference. So nothing very original here. You just rearrange them until you get them. Well, when do you ever need sine u sine v? Cosine u cosine v. Those kinds of things? Well, when you get the integration and you're doing products there, then you would do it. The product of sum formulas are used in calculus to solve problems involving the products of sines and cosines of 2 different angles. So, and most of those are made up problems themselves. Okay, I can't think of very many practical cases you need that. I'm sure there must be somewhere. Okay, so let's see if we can do example 7. So here it says, rewrite the product cosine 5x sine 4x as a sum or a difference. Cosine 5x sine 4x. What in the world would that be? I remember there's a 1/2 in front of it. And cosine sine comes from, you see those in your some angle for some formula for sines. Okay, it's the second half of that, right? So then that would be if you subtracted. So that's going to be a difference. And here it would be sine of 5x basically look it up. Yeah, it's 5x plus 4x minus the sine of 5x minus 4x. I think I got it right. Sum minus the difference. Got it. Okay, so what would this be? There's nothing really to calculate, just write it down. What is that? 9x minus sine of x. Okay? Now, I look at that and say, what good is that going to do me? I'm not sure, because I don't know what sine of 9x is anyway. They rewrite it like this: 1/2 of sine 9x minus 1/2 sine x. Sine x may not be a hard thing to deal with, but 9x, that's one of those multiple angles I'm not about to want to do too much with. Okay? So, but there they are. If you ever need them, there they are, how to use them. Look them up. Okay? I don't count it worth memorizing. I'm not a memorizer, so I don't even bother with that. Now, let's see how they did it. I think it's identical to the way we did, maybe a little neater. Use the appropriate product of sum formula. You obtain cosine 5x sine 4x is 1/2 of sine 5x plus 4x minus sine 5x minus 4x, which would be 1/2 of sine 9x minus 1/2 of sine x. Okay. Occasionally, it is useful to reverse the procedure and write the sum of trigonometric functions as a product. This can be accomplished using the sum to product formula. Now, this one, yeah. I would say if the other was rare to use, this one's extraordinarily rare to ever have a need for this. But here it is, if you need them. They're certainly not worth memorizing. Okay? So all I can say is there they are. If you need them, use them. The interesting thing here is, as long as you keep your U in front and D at the end, and the second, in all these, this one turns out being negative. It's the only one that does. The others are positive. Not to say that these things in here can't be negative, but the basic formula is negative. So again, definitely not worth memorizing. And let's do example 8, which they do not show. So let's go back and do example 8 here. Find the exact value of cosine of 195 degrees. Goodness gracious, get out of there. Cosine of 195 degrees plus the cosine of 105 degrees. Now, as you'll notice here, you have to really be careful when you're making up the problems in order to get to something that you can do an exact calculation with. And the thing that's magical about these two is what happens when you add those two angles. Anybody? What happens when you add those two? Not that hard to add. You get what? Add the two angles. What do you get? What do you say? 300 degrees. Now, that's pretty hot. No, I mean, that's, what is 300 degrees? That's way over in the fourth quadrant, 60 degrees short of all the way around. Well, there's your reference angle of 60, which is one of our favorites, right? Okay. And what happens if you take the difference of them? Difference of those two? 90, and that's another one of our favorites. Okay? But in order for this to be useful, that's the kind of thing you have to have. You have to have two angles that, even though you don't know what those are, they happen to be, the sum being one of our angles that we know, and the difference be one of the angles that we know. So there are not a lot of real practical applications for these, but when they are this way, then you might be able to do something. So what does the formula tell us? And again, I don't memorize these, so I go back and blatantly look them up. This is a sum of cosines, and that tells you that it's 2 times the cosine of the sum of the angles. And what are those sums? You did them earlier. That's 300. And it's not only that it has to be those angles, half of those angles have to be some of our favorite angles. It's 300 over 2 times the cosine of, and what's half of your other one? Well, the difference of those two is 90 degrees over 2. And this would be twice the cosine of, and what's half of 300? 150 degrees times the cosine of 45 degrees. Okay, so it's not just that the angles, the sum and the difference have to be our favorites. They don't even have to be. It's that half of them has to be, and 150 is one that we can deal with. Where is 150, Waldo? Okay. Second quadrant, and it's 30 degrees short of 180, right? Yep, there's a reference angle of 30. So what is 2 times the cosine of 150? Use that reference angle. What's cosine of 30? Nope. Sine of 30 is 1/2. Cosine of 30 is? Square root of 3. Only it's in the second quadrant, so it's negative square root of 3 over 2. And cosine of 45 is? Square root of 2 over 2. Pretty exciting, isn't it? Okay. So, let's see what happens here. One of the 2's goes out. You got 2 in the numerator, 2 in the denominator. And that leaves you with minus root 6 over 2. Yay! What an interesting thing to know. Yep, minus root 6 over 2. Okay? And by the way, there is a checkpoint for it too, so please follow up on that. Then there's example 9. And that's not on the slide set either, so let's clear this out of the way. Anyone need it up there a little longer? You got it, everybody? Okay. Then let's do example 9. And this one you can see larsonprecalculus.com for an interactive version of this type of an example. So here we have an equation. solve sine of 5x plus sine of 3x is equal to 0. Okay? It says for all values. No restriction, no limited domain here. So, how in the world are we going to do this one? Let's hope that we can use your product to sum formula, sine u plus sine v. That looks like it would be the case here. And what would that be? 2 times the sine of, which would be 4x, okay, times the cosine of x, no, yeah, x, because it's 2x over 2, cosine x, and we want that to be equal to 0, right? That's something I think we can deal with, okay? Certainly 2 is not equal to 0, so you can throw away the 2. Not going to enter the picture at all, okay? Now, so either we got sine of 4x equals 0, or cosine x equals 0. Now, where is sine of 4x equals 0? What would 4x have to be? Where is sine equals 0? Is that multiples of pi? Is that what you said? Yeah. It's an n pi. Exactly. Okay? So x would then be n times pi over 4. Okay? Every quarter of pi. Okay? Whatever n you put in there. Positive, negative, integer. Okay? Now, where is cosine equal to 0? Cosine x equals 0. Okay, it's pi halves and 3 pi halves, which are exactly pi apart, so plus n pi. We normally would say 2n pi for cosine and for sine, but guess what? They both of these happen to have every pi. Sine is 0 every pi. It's sometimes going up, sometimes going down, but they're all pi apart, and this is pi halves plus n pi. Every half pi is 0 again. So, if I'm not mistaken, this incorporates every one of those. Every one of them. So, actually, this answer should suffice it all. Let's see if it does. Okay. Yeah. Cosine x equals 0 yields all those half pi's, but they're all counted in your n pi over 4. So that's the answer that incorporates all of them. You don't have to list those others. They're already there. Okay. And you see when they did the graph here, you see it does hit exactly every quarter pi. Sometimes it crosses, sometimes it just touches, but every quarter pi is a 0. All right, any questions on that? All right, let's move on to applications, or at least an application. Ignoring air resistance, the range of a projectile fired at an angle theta with the horizontal, and an initial velocity of v0 feet per second is given by this function. R is equal to 1/16 v0 squared, that's your initial velocity squared, times sine theta times cosine theta. Now, if you're wondering where the 1/16 came from, remember you're at feet per second. And what is the acceleration due to gravity in the U.S. customary system? 32 feet per second. So this is exactly half of that. Not going to say how it wound up in the denominator, but that's where the 16 comes from. Where R is a horizontal distance in feet that the projectile travels. Okay? Says nothing about the total path length or anything else, or how high it goes or anything else. This is just R is the horizontal distance it travels. Also called the range of the projectile, and that's what you're looking for. If you're firing these projectiles from a ship or from a cannon or something land-based, you want to know what range. If you know where the enemy is, you want to be sure you get it that far. Okay. So, there's the setup. Where R is a horizontal, yeah, got it. Now, this time, it's not a weapon you're firing, it's a football. Football player can kick a football from ground level with an initial velocity of 80 feet per second. He can, I can't. Okay. Write the projectile motion model in a simpler form. Okay? So that projection motion model, they say write it in a simpler form. Now, let's go back to that. This has nothing to do with the football at this point. Okay? But write that in a simpler form. What's complicated about this? What makes it not simple? You have two trig functions. How could you write that? What relates sine theta, cosine theta with the one that only has one trig function? Yeah, not really. Think. What?
The sum and difference.
Okay, getting close. If those two angles are the same, that you're doing the sum or difference of, preferably the sum. What?
Sum and product.
Yeah, the product is the double angle formula. How does that go? Which one of them has sine and cosine in it? Sine of 2 theta is equal to what? Isn't that it? Yeah. Sine of 2 theta is twice the sine theta cosine theta. You get that from the sum angle formula. Sine of A plus B is sine A cosine B plus sine, cosine A sine B. Okay? And then if A and B were the same, okay, then sine of 2A would be sine A cosine A plus sine A cosine A sine A, which is 2 sine A cosine A. So there's your sine of 2 theta. So, if and rather than sine theta cosine theta, if we take half of that and make it this, so take half of what's written there, that would be R is equal to 1/32 V0 squared times sine of 2 theta. Is that not right? Instead of sine 2 theta, if we put 2 times this, 2 would likely that would give us the same. So that's that written in a simpler form, right? And that's a little bit nicer, except you got a 2 theta. Okay. So we've done the first part. irrespective of football player or anything else. Okay. So there was the first part. R is equal to 1/32 V0 squared sine of 2 theta. I assume that's what we wanted. It's simple. Now the question, at what angle must the player kick the football so that the football travels a 200 feet, which, by the way, is 66 2/3 yards. Sign him up, Nick, okay? Especially if you can do extra points. Never mind, we won't go into that, okay? So, what would we do to do this then? Put the R equal 200. So 200, I'll put the units in, I'll probably regret it later, is equal, I will regret it because the 32 has units with it and I don't even want to mess with that. And what was our V0? That is 80 feet per second, but we're going to square that, okay, times the sine of 2 theta, okay? We're going to be solving for theta because that's at what angle. That's going to be the answer that we have. All right, well, let's proceed. What is 80 squared? $6,400. Divide that by 32 and you get $200. So what we have then is 200 is equal to 200 times sine of 2 theta. Okay? Divide both sides by 200. And you get 1 is equal to sine of 2 theta. Okay, now where is sine of what angle is equal to 1? Pi halves, exactly. So 2 theta must equal pi halves. So guess what theta would be equal to? Yep. Pi force. And every time you went to kick, you went through this in your head, didn't you? No! Think how much better you could have been. Okay. But this is true, isn't it? The longest range is at that 45-degree angle. You kick it higher angle, you go higher in the sky, but you don't go as far. Kick at a lower angle, and you don't have enough height to go as far, okay? So either one of those will produce something less. That is the maximum. Now, extra points, you should kick pretty high. You're right there in front of the goalpost, right? So the higher you kick it, the less likely to be blocked. Nick, pay attention, okay? All right. Didn't he have, what, 2 blocks against LSU? Did anyone watch the game? That's the Braves hat. It's not Alabama hat, isn't it? Okay.
I watched like half of it.
What's that?
I don't know if they got any block. I know they missed one.
Oh, they just missed it?
I watched half of the game, so I don't know.
Yeah. We went to the UAB game, so we missed the first half, and that's when I think one of them was missed, and I think one got blocked. I'm not sure, but yeah. Anyway, so we just heard about it. Someone's going to get chewed. But yeah, at what angle? Pi force, 45 degrees. Okay. That's where you get your maximum range, by the way. All right, any questions? Oh, let's see. Let's watch how they did it. I did all the talking there. Let's show how they did it. Okay, first, you can use the double angle formula to rewrite the projectile motion model as that. First thing they did, they multiplied numerator and denominator by 2, which is very insightful because then 2 sine theta cosine theta is sine 2 theta. Okay, so we got the same thing. We didn't quite do it the same way. Okay, and then using that, write that. Yay, I would write it again, and then plug in 200 for your range, 80 for your maximum velocity. When you do the math, that comes at 200 equals 200 sine 2 theta. So 1 is equal to sine 2 theta. 2 theta must be pi halves because that's where the sine is 1. And then divide that by 2 and you get theta equal pi fourths. Now it's also 1 at 5 halves pi, but you don't do much kicking of field goals at that kind of angle, do you? No, let's not do that. Nick would really be on your case if you did that. Okay. So, because theta, pi fourths is 45 degrees, the player must kick the football at an angle of 45 degrees so the football will travel 200 feet. But that also increases the likelihood that they could get their hands up and block it, which I think is what happened at a game against Auburn a long time ago, if y'all remember that one. All right, but we won't go into that. There is a checkpoint there. Please do the checkpoint. Let's do vocabulary. Top of page 388. Sine of 2u is what? As if we hadn't just done that one. 2 sine u times cosine u. Perfect. And cosine 2u is? Cosine 2u. Yes, cosine squared u minus sine squared u. Number 3, sine u cosine v is, yeah, like I remember that one. Turn back to the table and look it up. You got it, okay? And 1 minus cosine 2u over 1 plus cosine 2u. What's that equal to? You have to go even further back. That's tangent squared u. Perfect. Then number 5, sine of u over 2 is plus or minus the square root of 1 minus cosine u over 2. That's under the radical. And cosine u minus cosine v, yeah, that's one I remember all the time. What's that? That's the negative 2 sine. Perfect. Perfect. All right. So let's, homework exercises here. Do any of the odds 7 through 13. They're all at calcchat.com. 9 is at calcview.com. Then you do any of the odds 15 through 19. They're all at calcchat. Do any of the odds, do either 21 or 23. They're both at calcchat. 21's at calcview. Try to do number 25. Okay. It's one like what we did before. Then do any of the odds 27 through 33. They're all at calcchat. 27's at calcview. Do any of the odds 35 to 39. They're all at calcchat. 37's at calcview. Do either 41 or 43 or both. They're both at calcchat. 41's at calcview. Same thing with 45 and 47. They're both at calcchat. 45's at calcview. Same with 49 or 51. They're both at calcchat. 49's at calcview. Same with 53 or 55. They're both at calcchat. 53's at calcview. Same with 57 or 59, except they're both only at calcchat. Neither are at calcview. 61 and 63, they're both at calcchat. 63's at calcview. Then any of the odds 65 to 69, they're all at calcchat. 65's at calcview. And then the interesting, one of my favorite pictures of all time, number 71. Is talking about breaking the sound barrier and dealing with that. That's a fun problem to do. Railroad tracks, 73. True false, 75. They all should be at Calc Chat. 77 is the last one, and that's at Calc Chat as well, if you choose to do it. You don't have to. There is a chapter summary here if you want a brief look at all those formulas we ran into, or just about all of them. There's some review exercises that you can do any of these if you want. The odds are at Calc Chat. I think all the answers are in the back of the book, but only the odds are at Calc Chat. And they go by section, so if you need any more exercise there, the odds are at Calc Chat. Then there's a chapter test. I think all the answers are in the back. However, only the odds are at Calc Chat, and you can certainly look through those. All right, that finishes Chapter 5, which means now you get the bonus of the test for Chapter 5. And I'm trying to remember how many of the second test I've gotten in. Maybe 0. Okay? So please, folks, let's get those back in. Anyone not get the second test? All of you got it? Okay. And let me find the third test. I think it's right here. Okay. Okay. This one, I don't think there's any graphing on. I think you got plenty of graphing on the last one. This is just please try to get these. Actually, that second. I do believe there may be. And I may still be missing some test ones, am I? I gotta look at my book real quickly. I think I must be here. I was referring to you. How are we doing on time? I don't have my watch with me. Plenty of time. Okay, good. I love to hear that enthusiasm. Okay, so let's get out of this. 5 minutes. We've got time. So I think I put these upside down. These all messed up. Okay. Let's get started in Chapter 6. We've got some time. Let's do it. That's not what I wanted to do. Okay. No, that's not what I wanted to do. That's what I wanted to do. All right, Chapter 6. And as soon as you see the title, you'll know this is sort of a catch-all, okay? Believe it or not, Chapter 1 was fairly focused, though it covered a broad range of things. Chapter 2 was somewhat pretty focused. It all dealt with identities and analyzing trig stuff. Chapter 6 is pretty far-fetched. Some things are related, but a lot of the things are not that much, okay? These are just additional topics in trigonometry. The first two are pretty much related. The next two are pretty much related, and then the last two are pretty much related, but not too much in between. So let's start with the law of sines. Now, up till now, when we've had triangles, what kind of triangles have they been? Right triangles, okay? The law of sines and law of cosines gives you way to solve oblique triangles. What oblique means is not having a right angle. They can have all acutes or one obtuse and the other two acute. Those are oblique triangles. Your other techniques will not work for them. These will. Now, they give them little initials here. And what these stand for are angle, angle, side, or angle, side, angle. So if you're given two angles and a side that's not in between, or two angles with the side in between those, opposite those angles, either one of these you can use the law of sines. And here's why. If you know two angles, no matter what two angles they are, guess what you know? The third angle as well, because the three angles that, so those are obviously going to be law of sines. And the reason for that, you have to have an angle at this opposite side. If you have that, you can use the law of sines. Now that also works for side-side angle. And we never call this angle side-side for obvious reasons. Okay? We don't like that abbreviation. Never mind. But we'll use the law of sines to solve oblique triangles when you have side-side angle. Now this one you can't automatically have, but what you do have, one of these sides is opposite that angle, so you can use the law of sines there. Okay, this, you know all three angles, so that side is going to be opposite. Either side is going to be opposite one of the angles. Okay. But something very similar is then finding areas of oblique triangles. It doesn't use the law of sines, but it looks enough like it put in with that. And then we'll use the law of sines to model and solve some real-life type problems, which is what we love to do. Okay. So, how are we doing? Still some time? Huh? 1 minute. Okay. Let's, I guess, stop there, and we'll begin with the introduction here, top of the page. That's where we'll begin on Thursday. We'll get as far as we can in this chapter. There's 6 sections. We don't have all that much time left, but that stuff at the end we can probably live without. Complex numbers we don't really do that much with. So take care. Oh, if you haven't voted, you have till 7 today. Please vote. Please vote.